Welcome to the deep dive. We cut through the noise, get you those essential insights, the stuff you need to be truly informed. Today we're diving into something, well, pretty groundbreaking from Google. It's called AlphaEarth Foundations. Think of it like a virtual satellite, one that sees pretty much everything everywhere all the time. So our mission here is to unpack why this was even needed in the first place. How does it actually work? What problems is it solving right now in the real world? And what could it mean for big things, like monitoring crops or even fighting climate change? We're basing this on an article called AlphaEarth, a virtual satellite for climate action by ASMAT, published August 1, 2025. Okay, let's unpack this. So maybe let's start with the why. What's been the biggest headache for Earth scientists? It sounds kind of backwards, but they're almost drowning in satellite data, right? But they really struggle to get one, coherent picture of the planet. Too many pieces, maybe.
Exactly. And it's not just the volume, it's the incompatibility. That's the real killer. You've got images coming in at totally different times. Like one satellite flies over every 5 days and maybe every 16.
Okay.
Then the sensors themselves are different. Radar, it slices right through clouds. Optical, it just bounces off.
Right. Useless on a cloudy day.
Pretty much. And then you add in, different pixel sizes, weird orbit quirks, calibration differences between sensors. It's a mess. It's not just one puzzle. It's like 1,000 different puzzles thrown in the same box.
And these gaps, these blind spots, they have real impacts, don't they? What kind of frustrations does this cause, practically speaking?
Oh, huge frustrations. Think about crop analysts. They might wait weeks, honestly, sometimes months, just for a decent cloud-free view.
Wow, weeks.
Yeah, and that's critical time lost for agriculture. Or conservation teams may be juggling 5 different land cover maps. None of them quite agree on where a forest boundary is, for example.
Yeah.
And city planners, they're trying to combine nightlights, population data, traffic feeds, all from different places, different times, and just hoping their assumptions kind of line up. It's a massive challenge. It slows down really critical decisions.
Okay, so that's the problem. And this is where AlphaEarth Foundations comes in. The article calls it a quiet librarian, which I think is a great analogy. Can you unpack that? What does AlphaEarth actually do?
Yeah, quiet librarian is good. At its heart, AlphaEarth Foundations is what we call a geospatial embedding model. Okay, so an embedding, it's basically a compressed numerical fingerprint of complex data. Instead of looking at, a whole mess of raw images and sensor readings for some patch of land, AlphaEarth processes all that, petabytes of it. Optical, radar, LiDAR for tree height, climate data, even text from Wikipedia.
Wikipedia.
Yeah,
Oh.
geotagged context. And it distills all of that down into this compact 64-number vector, a fingerprint, for every single 10-meter patch of land and coastal water on Earth.
So it's not actually in orbit, but it acts like a satellite because it's pulling everything together,
Yeah.
synthesizing it.
Exactly. That's the virtual satellite idea. It doesn't orbit. It synthesizes. It acts like this consistent, always-on observer. It can see through haze. It understands seasons. It remembers past events, like a drought last year, while also monitoring what's happening right now, like soybeans starting to grow. It's like this super smart eye sorting out the chaos.
And these fingerprints, these embedding, they're tiny, right? The article says 16 times smaller than previous attempts. How important is that size difference?
Oh, it's huge. That's a key design choice. And it's what makes AlphaEarth practical, not just, an academic paper. Because they're so small, you can actually use them easily on platforms like Google Earth Engine. You don't get that storage shock.
Wow.
You're not trying to download and manage petabytes of raw data yourself. It means you can basically start working with it instantly. It's ready-to-use infrastructure.
Okay, here's where it gets really interesting. Let's do a lightning tour of how it actually works. The source talks about this rolling cube of space-time. Can you help us visualize that?
Sure. Imagine a square on the ground, 10 meters by 10 meters, like a small part of a field. Now stretch that square upwards, but through time. So it covers a whole year. That's your cube of space-time.
Got it. Space and time combined.
Right. And into that cube flows just a ton of data from all sorts of sources.
Yeah.
You've got Sentinel-2 visual images, Sentinel-1 radar, Landsat thermal data, GDI LIDAR for canopy height, GRACE measuring tiny gravity changes, ERA5 land climate data, and like I said, even relevant bits from Wikipedia tied to that location.
Okay, so all that data goes into the cube. Then what?
Then a self-supervised encoder looks at everything inside that cube. It learns patterns, like how certain colors, the spectral signatures tend to line up with the terrain, or how radar signals shift when rice paddies get flooded, or even how, say, a Wikipedia mention of a peat bog matches up with specific moisture patterns the sensors see. Then there's this clever compression step. It takes all that raw, messy info and boils it down into that neat 64-number embedding.
And somehow, that tiny embedding still knows about things like moisture or how tall the trees are, even without storing the original pictures. How does it stay accurate after squishing it down so much?
Good question. There are these, let's call them consistency checks, built into the training. One basically ensures that even if some data is missing for a spot, maybe clouds block the view that day, the embedding stays stable, it looks like it would if all the data was there.
Okay, makes sense.
The other check makes sure these fingerprints are spread out sensibly in the model's numerical space. So when you compare two fingerprints, how close they are numerically actually means something about how similar those places are on Earth. It helps the model organize things properly.
So the result is this smooth, really dense map of Earth that anyone, biologists, water experts, city planners, can just query.
Right.
Instead of wrestling with data feeds, you could say, spot sugarcane spreading just by looking for shifts along certain numerical axes in the embeddings.
Exactly. Or calculate something complex, like evapotranspiration for a whole county, which is vital for water management, using just a really simple model on top of the embeddings.
That sounds like a total game changer for how people interact with Earth data.
Hmm.
Let's talk about some early real-world examples. Pilots. That's where you see if it actually works, right?
Definitely. There's a fascinating one from the Amazon about detecting pasture creep.
Pasture creep.
Yeah, it sounds kind of minor, but it's actually a super early warning sign for deforestation. The embeddings picked up these subtle changes in texture from the radar data way before you could see any trees being cut down in normal satellite pictures.
Wow, an early warning system.
A crucial one. Another example, the UN's FAO biochar team used it. AlphaEarth helped them find leftover corn stalks in fields, stuff that older methods kept mistaking for just bare soil. That's important for, sustainable farming practices.
That's really impressive. Makes you think about how this changes mapping itself, moving from just like pixels on a screen to actual policy decisions.
It's a massive shift. Think about traditional mapping. It's usually bespoke, siloed. You pick a topic, say, forest cover, download tons of data, train a model, publish one map for 1 year. And its legend probably doesn't match anyone else's map.
Right. Everyone doing their own thing.
Yeah. AlphaEarth, or geospatial AI using embeddings like this, flips that completely. Instead of thousands of custom maps, you get one foundational numerical layer, and you can ask it almost anything. That universality is key for climate change AI, where you have to connect different things, deforestation, temperature, rainfall. For instance, the article mentions AlphaEarth reproduced a global emissivity map, basically how surfaces radiate heat, with less error than the original hand-tuned methods.
Wow.
And it matched a big evapotranspiration data set using something like 400 times less computing power. It's like the source says one network to learn them all, but here the network describes the whole planet. And just digging under the hood a tiny bit more. A single model looks at 9 different types of satellite data plus Wikipedia text, covering, get this, 1.4 trillion 10-meter spots every year.
That number is staggering.
It is. And the training. Only 56 hours on specialized hardware, TPSU V4s. That's like 2.5 days. It's incredibly efficient for what it does, and each embedding, that 64-number fingerprint, it's a point in this complex, high-dimensional space. But the cool thing is how they relate. Similar places, like healthy forests, end up with fingerprints that are numerically close, even if they're continents apart.
So there's a structure to it.
Exactly. The distances mean something. It lets the model find real clusters and patterns on the Earth itself.
So maybe the philosophical bit here
Yeah.
is that these 64 numbers aren't just compressing data. They might be revealing something simpler, more fundamental about how Earth systems work.
That's the implication, yeah. It suggests there's this hidden lower dimensional structure, this manifold connecting climate, vegetation, human impact.
Yeah.
And discovering and navigating that structure. Well, that's kind of what geospatial AI is all about.
It sounds like making this accessible was a really big goal. Putting it on Google Earth Engine, how does that specifically help, say, smaller groups or researchers without huge computers?
Oh, it's absolutely a game changer for accessibility. The embeddings are just there, a public asset in Earth Engine. No need to download petabytes, no complex pre-processing like cloud masking. You just grab the embeddings and start building your models right there in the platform.
So it lowers the barrier to entry significantly.
Massively, especially for, government agencies in developing countries or university labs, groups without giant GPU clusters. And honestly, many people can get started really effectively with just a simple linear model because the embeddings themselves have already done so much of the heavy lifting, combining all those different data sources.
And the results, the performance numbers, Seem pretty stunning. Can you give us some highlights, maybe without the academic jargon?
Sure, let's see. For land useland cover mapping, it cut error rates by about 25% compared to older methods using stacked satellite bands, and about 33% better than another AI model, SAT-CLIP. And that was using only about 1,000 labeled examples, which is tiny for training.
Okay, that's impressive with so little training data. What about something like crop types?
Yeah, for Canada's national crop inventory, that's a tough one. 24 different crop types. It hit 86% accuracy with just 500 training points per class.
Yeah.
That beat carefully handcrafted features, and it did it using embeddings that are 16 times smaller data-wise.
Well, and water usage, evapotranspiration.
Right, measuring water loss. Compared to a big ensemble model called OpenIt, AlphaEarth got an R² of 0.58 at that fine 10-meter scale. The next best baseline was way down, below zero point 0.2, so a huge leap in accuracy there.
Okay, and change detection, seeing how land cover changes over time.
Nailed it. 79% balanced accuracy for tracking land cover changes in the U.S. And it did this using just a simple threshold on how much the embeddings changed over time. No need for complex, region-specific adjustments or tricky ways to fuse radar and optical data. It just worked.
Okay, but like you said, no model's perfect. AlphaEarth must have some limitations, right?
Absolutely. And it's important to know them. For example, deep in the tropics, really cloudy areas, it can sometimes confuse cloud shadows with actual land cover changes.
Okay, so what do you do?
Well, you can work around it. You could blend the AlphaEarth embeddings with data from satellites like PlanetScope, which image much more frequently, like daily.
Got it. Any others?
Yeah, really small urban features like tiny buildings or roads might get smoothed out at the 10-meter resolution. A workaround there is maybe fine-tuning with super high-res aerial photos for a specific city, then kind of distilling that knowledge back into the main embeddings.
Makes sense.
Snow cover seasonality can sometimes lag a bit in the standard annual embeddings, but they're planning quarterly releases, or you could just average the monthly embeddings yourself.
Okay.
Coastlines, especially out in the open ocean, are a bit underrepresented right now because the training focused mostly on land. So adding specific ocean color data, like from Sentinel-3, could help there. And even the Wikipedia text input, it has biases, right? It knows more about well-documented places. So you can maybe swap in local field notes or species sightings from databases like GBIF to provide more grounded text context. Knowing these things helps teams decide, when to just use the embeddings straight up versus when to maybe add in some extra data or a custom feature.
So we know where it is now and what it can't quite do perfectly yet. But those limitations, like you said, they point towards new research, right?
Yeah.
What are some exciting next steps you see for AlphaEarth?
Oh, yeah, lots of potential. I'm watching 5 areas pretty closely. First, those quarterly embeddings, that 4 times increase in temporal resolution, huge for things like tracking crop growth or wildfire recovery.
Definitely.
Second, imagine running parts of this on small devices, edge sensors, like a Raspberry Pi out in a remote field station. That gets feasible if they optimize the model, maybe with a tiny hit to accuracy.
Real-time monitoring on cheap hardware.
Third, linking it with large language models, LLMs. Embeddings are numbers, people need sentences. So hook AlphaEarth up to an LLM, and it could automatically write briefs like, Alert, Northern Shanxi lost 3% of its maize crop in June due to hail damage.
Wow, automated reporting.
Fourth, using citizen science. Imagine hikers uploading geotagged photos of, say, a misclassified forest patch. AlphaEarth could potentially use that feedback to subtly adjust its understanding locally without needing a full retrain.
Closing the loop with ground truth.
Exactly. And fifth, benchmarking for AI and climate change work. We don't really have a standard way to compare models for things like carbon emissions, biodiversity loss, disaster risk. Embedding fields like AlphaEarth could provide a common ground, a fair leaderboard to track progress.
And just to make this really practical for a moment, imagine you wanted to build, say, a simple crop monitor. How easy is it with this? The article gives this day zero guide idea. You could apparently flag stressed wheat fields, maybe 3 weeks before harvest, with less than 100 lines of code in Earth Engine. And it runs in like 8 minutes for a whole province, skipping all the usual complex steps.
That's the promise, yeah. It sidesteps a lot of the traditional, really time-consuming remote sensing workflow, dealing with clouds, calculating vegetation indices, figuring out seasonal growth curves. The embeddings handle a lot of that complexity implicitly.
So it plugs into this whole ecosystem.
Right. It works within Google Earth Engine. It's part of their Earth AI packages, but you can also export it.
Yeah.
Use it in standard GIS software like QGIS or ArcGIS as if it were just a 6v4 band image. Or if you're a Python coder, it's just a NumPy array. That ecosystem connectivity is key. It lets the water expert, the agriculture expert, the forest expert finally share this common computational language. It breaks down those silos we talked about.
And that brings us back to the really big picture, fighting climate change.
Yeah.
How does AlphaEarth fit in there?
Well, climate modeling is all about these complex feedback loops, right? Deforestation changes how much sunlight is reflected, which affects rainfall, which impacts crops, which might lead to more deforestation. It's all connected.
Right.
AlphaEarth helps models capture those loops much better and faster because all the key variables, the trees, the water, the human activity, they all come from the same underlying representation. So think about a tropical nation trying to manage its resources. A policy model could ingest deforestation risk, weird patterns in water evaporation, maybe increases in nighttime lights indicating development, all from AlphaEarth without juggling different incompatible data sets. That means faster insights, better decisions, quicker monitoring, and really importantly, audits that you can actually reproduce and verify.
Okay, but even with this amazing global layer, do localized, personalized models still have a place?
Oh, absolutely. AlphaEarth is this incredibly powerful base layer, like a foundation. But local teams will definitely still build their own specialized detectors on top. Things like, spotting a specific type of coffee rust disease in Ethiopia, or tracking beaver dams expanding in Canada, or making super detailed soil carbon maps for precision agriculture.
So you build on AlphaEarth, not replace everything else.
Exactly. You treat AlphaEarth as the foundation, and then you add what are called thin adapters, small focused machine learning models on top. So say a field crew collects just 200 soil samples, they can train a tiny model using those samples and the AlphaEarth embeddings for those locations. And suddenly that model can generalize, make good predictions across a much wider area in a way that used to need maybe 20,000 samples.
Because AlphaEarth provided the context.
Precisely. The heavy lifting, that deep understanding of the landscape's patterns, is already baked into the embeddings.
And we're seeing real stories, anecdotes from people using this already.
Yeah, some really cool ones. A startup in Jakarta apparently used AlphaEarth embeddings with a simple model, predicted flood-prone areas with 88% accuracy, and they did it 2 months faster than their old methods.
2 months faster.
Huge difference. And a biodiversity group in Madagascar. They used it and found 6 patches of coastal forests that were basically missed on previous maps. Now they can try to protect them.
That's amazing, finding lost forests.
Right. And an insurance company in Portugal modeling wildfire risk found that changes along one specific axis, number 51 of the embedding, that was actually a stronger predictor of risk than traditional things like the slope of the land.
Wow. So it's finding non-obvious connections.
Exactly. And the really striking thing is a lot of these successes are coming from teams outside the traditional high-end remote sensing labs. It really proves that when you lower the barriers to using this kind of powerful data, you just unleash a wave of innovation from everywhere.
You had a wish list for AlphaEarth version 2. What would be on it?
Okay, my personal wish list. First, an open weight release. Let academic labs really dig in and build upon it. That would be huge.
A good one.
Then I'd love to see nightlights integrated directly, maybe data on air pollution, trace gases from Sentinel-5P, get more of that human activity fingerprint in there. Real-time updates would be incredible for disasters. Imagine getting delta embeddings, just the changes, right after a new Sentinel-2 image comes down.
Wow. Near real-time change detection.
Yeah, and a proper seamless extension out into the oceans, covering sea surface temperature, chlorophyll levels, maybe even wave height. Oh, and built-in uncertainty flags. So for each pixel's embedding, you get a little score saying how confident the model is about that particular spot.
Knowing where it might be guessing.
Exactly. But I'm optimistic. The teams hinted at quarterly updates, tighter links to language models, so I think a lot of this is probably on their roadmap, too.
So let's try and wrap this up. What does AlphaEarth Foundations really mean? It's not just another map, is it?
No, not at all. I like the analogy of a scaffold. It's like a framework that holds all the other maps together, makes them consistent. Or you could think of it as like Earth's compressed autobiography, updated yearly or maybe quarterly soon, and readable by pretty much any AI pipeline. It feels like the culmination of decades of work in geospatial AI finally becoming, really practical and actionable.
And the payoff seems clear.
Yeah.
Speed, simplicity, and the potential for genuinely surprising insights about our planet. So the call to action for you, our listener, if you work anywhere near conservation, agriculture, disaster relief, city planning, anything that uses satellite data, the message seems to be, grab these embeddings, they're public. Try putting even a simple model on top. See what the planet tells you through this new lens. Chances are, AlphaEarth might show you a pattern in minutes that used to take months to find, if you could find it at all.
And maybe a final thought to leave you with. May your next model train faster, map cleaner, and genuinely help nudge us all towards a more climate-wise future.